Done? Fun, good. That's good. It should be fun. I'm glad that you're finding it fun. I think that's an important reason to be doing computer science in general, is if you think that programming things and building things is fun. Any questions about it? Any concerns? Anything I need to know about? No? Yeah?
The dot heuristic is hard.
The dot?
Yeah.
Which one is that?
The dude one. Yeah.
The what? The dude one?
You have to eat all the little dots. The not corners one.
I see. Yes. Yeah, you have to think about how, so somebody posted a question on the discussion forum about that one. You kind of have to think about how you define your state space in order to come up with a good heuristic. I think the trickiest thing about it is the state space. So it's question 5, building on question 6 on the problem, on the project. So just so you know, we decided, I think there's been enough attrition with the first homework and stuff that we're going to be able to fit everybody in this room. So we're still going to put the lectures online. We've been doing that. I think we've got all the YouTube problems ironed out now with that, but we're not going to have the live streaming upstairs. So I think that's good because we can all be together and you can all ask questions and stuff like that. And I encourage you again, I'd like to encourage you guys again to continue posting on the discussion forum. I saw that a couple of you did, and I wrote responses this morning to the questions. And I think it can be a really good resource, not just for interacting with the course staff, but for pairwise interactions with each other. So it'll let you guys benefit from the awesome student population that we have here in Brown, because you can sort of form those peer-to-peer interactions. So I actually wanted to start by highlighting one of the questions that got posted on the discussion forum, because I think it's a good segue into the topic for today's class. So this was the question. Say we perform simulated annealing in a 2D real space. Do we randomly choose a successor from a uniform disk or from a Gaussian, or doesn't it matter? Or where's that successor coming from? So does anybody want to respond to that in some way? Where do you guys think the successor comes from? What do you think? Do you think it matters? Yeah. Sure. Yeah.
Yeah, if your temperature function decays exponentially, then you can have a uniform.
Yeah.
And the overall effect will be sort of exponential.
So remember from last time we were kind of combining the temperature function with, so in our discrete state space, we were uniformly sampling from the next action. And then we were weighting it according to our temperature function. So here the question is, should we uniformly sample from a disk, which is basically what I was doing last time. I was defining a disk of 0.5, and I was discretizing it in increments of 0.5 and 0.25, and then I was uniformly sampling from the disk. So what would it look like if instead I sampled from a Gaussian? Well, first of all, what's a Gaussian look like? It's my, where's my whiteboard marker? So it's like an n, and if I draw a picture, it's a probability function, so it has to integrate to 1. And it looks like a little hat. It's like your bell curve, okay? So how do I parameterize a Gaussian? There's 2 numbers that I can use, standard. That's 1. Mu, yeah, those are the traditional variable names. So I write the variable names down. So n of mu and sigma. So anybody want to say what those variable names mean? So what is mu usually? Mean, yeah. So if I'm want to draw that, so mu is the mean. If I want to draw that, what is that going to be? It's going to be a little point on the x-axis. Where? Not you, somebody else. Thank you, though. Yeah.
Right in the middle of.
Right in the middle of the hump, yeah. So this is mu. And then what's my sigma? Yeah. Standard deviation. So how am I going to draw that? You in the back there. You put your hand up. How do I draw a standard deviation?
From the mean.
Yeah, I had these little bars going out from the mean. So like from here to here. And this is my sigma. Okay? Yeah, there's seats in the back, and we're no longer doing the upstairs room. I think we can all fit in the middle. Although, Pat, can you count? About halfway through the class, just count how many people are here so we know. All right. So what's so the question here was about a 2D space, but we can think of so you can imagine like that example from last time where there's an x and a y that you're sampling from. But you can ask and a 2D Gaussian, the sigma would be like an ellipse. right? I'd be going in x and a y. But I can also do it in this 1D, in this line space. And I could imagine with my example from last time, sampling from a Gaussian, just sampling my x from the Gaussian. So how would that be different from sampling from a disk? So first of all, where do my parameters? Let's actually write down the parameters of my disk sample. So my disk, what does that distribution look like? You. Yeah, it's like a box, right? And then in my example from last class, it was actually like a delta function, right? It was discrete. So if my point was right here, I could sample from 4 different new locations. I could go 0.25 and I can go 0.5 or 0.25 or 0.5. But if we're gonna let's sort of think about a continuous space, it would be a box. Okay, so I could sample uniformly from within that box. I don't really need to have this discrete action space, and sort of so it would be here and then it would be 0 everywhere else. So what's the difference between these two? Yeah. The Gaussian is infinite, yeah. So depending on my sigma, even not depending on my sigma, like no matter what my sigma is, I have the potential to sample anywhere on this number line. So I could potentially consider a really, really big move. I might do it with very low, I might only consider big moves with low probability. So what would my parameter values have to be for me to consider? So first of all, for the Gaussian, where's my mu going to come from in this world? Karthik? From my current location, my mu is given to me, right? I want to sample close to where I am. I guess you could do something else that would make you like sample far away. Like if you did your current location plus 100, it would be like, well, where I am is not where I want to be next. Wherever I am is bad. Kind of the depressing algorithm, like forever unsatisfied. But we're going to say our mu is always where we are right now. So what is the other parameter sigma gonna do? So yeah.
It's based on temperature, based on how closely you want to look.
We're on. I mean, the temperature is kind of. We're not even at temperature yet. So this is first just selecting the action. Once we've selected the action, then we can use our temperature to compute whether we're going to accept that move. But first, this is kind of like a proposal distribution, where we're going to draw a move that we're just thinking of. We're going to think about it. When we think about it, we're going to use the temperature. We're going to use the cost, like we did last time, to see whether we like it or not, with some probability. But this is just a proposal distribution. Make sense? Yeah.
So if sigma is small, you're more likely to say close by. If sigma is big, you're more
That's right. Exactly. So if sigma is small, my Gaussian is going to be really, really peaky. It's going to be like this. Only it's going to be like a Gaussian and not with my random scribbles that went wrong, right? It's going to be very peaky. It's not going to, there's going to be some probability mass all at the infinities, but it's going to be very small. It's very unlikely that I'll make one of those moves. If my sigma is big, I'm going to have a really big, wide Gaussian. Again, it'll be normalized, so it's something on that, so it probably wouldn't be up like that. But it'll be really wide, and I'll be more likely to make a big move. So what's the analogy of that in this guy? So what's the parameters of this thing? Yeah. The radius, yeah. So like, I don't actually know if there's a standard variable name for it, but let's just say r. How wide my distribution is going to be. Once I know how wide it is, I know how tall it is because it has to sum to 1. So because the area has to be 1 or it won't be a good probability distribution. So what happens if my area is really wide? If my radius is big? Yeah. Yeah, I'll give a wide range of successor values. But so now let's think about what's the difference between these. And if it's really small, I'll have a really narrow range, right? So here's a narrow range and here's a wide range. And the Gaussian would be like that too, like a narrow, tall range and a wide, short range, again, to make it normalized, but I just didn't draw it to scale. So the Gaussians aren't to scale, don't let that bother you. Okay, so now what's the difference between these two? So I have the same, in both instances, I have a parameter, and if I make the parameter big, I have a wide range, and if I make it small, I have a narrow range. What's the difference? Yeah.
The Gaussian is much more likely to pick nearby successes.
Well, I think you kind of have that too, though, right? Because we're here. It depends on what our parameter is, right? But like I could sort of imagine a wide distribution and a wide Gaussian. So this long flat one and this big flat Gaussian here. where they're kind of doing the same thing. They're kind of biased towards that same part of the probability space. So there's an even bigger difference, I think. Somebody in the back I saw? No? Here.
But isn't the Gaussian, you're more likely to pick a point next to you compared to the uniform distribution where any point is equally as likely? 'Cause it's uniform.
Yes, right. So because you've got this peak that falls off, you're more biased towards the ones that are close to you. But what about the tails? What's the tail in this distribution? Yeah.
You could have a lot more extreme choices in the Gaussian.
Yeah, you might get a lot of really extreme proposals. So the question was like, well, what's the difference in using a uniform disk or a Gaussian? I think I don't actually know, like for sure. So to actually know for sure, we'd have to like prove a convergence bound on our simulated annealing algorithm. And people do that, and it involves like a lot of math, and it's actually like proving how fast these stochastic algorithms converge in these kinds of situations is an unsolved problem for a lot of examples. So there's active research in machine learning for proving performance bounds. For this particular example, I suspect it's possible to do it without that much trouble, but I haven't actually done it. So I'm hypothesizing that the Gaussian would converge faster because it's allowing these much bigger jumps, and so it'd be more likely to get to a better space in its sampling. But I suspect, sort of following from the results in the textbook, where they said that if you just lower the temperature slowly enough and run it long enough, that they would both still converge. So I think what the difference would be here is you would in both cases, if you ran it long enough, if you ran forever and ever and ever, you would get you'd get the same correct optimal answer, or locally optimal answer. But the Gaussian might be faster to converge, and there might be it might be faster to converge because it's making these bigger jumps. So it might be better, easier for it to get out of these big humps. But it probably depends on the parameters. So I hope, okay, so that's kind of like, and a lot of what the magic or the art in these stochastic algorithms is selecting what you're doing when you're making these proposal distributions. And you can do a lot better in terms of algorithm performance and in terms of making it converge more quickly if you select where the successors come from in a smarter way, in a more informed way. So this is kind of an uninformed way, right? Either one, Gaussian or the uniform disk, is kind of uninformed. I pick some parameter for how wide my search is, and I'm just going to draw some samples and hope it works out. So what I wanted to talk about in class today was one particular example of a way to select where to go, to update your model parameters in a more informed way. And we're going to kind of change the pace of class a little bit. So I had you guys over email to read this research paper. Who read the paper? Good. All right. So what did you guys, so I didn't actually get to this slide last time, but I tried to put some of this in the email that I sent. This paper includes a lot of material, and there's a lot of stuff going on, some of which we're going to cover in class, some of which we're not going to cover in class. It's called reinforcement learning, which is like we're supposed to cover in like the way end of the semester. And it's got machine learning, it's got a lot of stuff that we haven't actually hit yet. So what I wanted to say to you before we dive into what it is and how it's working and what they're doing is why I asked you to read it now, like at the beginning, before we've covered this material. So my goal in having you read this paper now was to give you a sense, first of all, of how some of the ideas that we're talking about play out in real-world problems. And I hope we'll talk about, in particular, the way that they formulated the problem and defined the search space. I hope that felt very familiar based on what we've talked about so far. And the way that they sort of had this way of going from the current state to the next state. So the first thing is I wanted you to see how some of those ideas applied in the real world. There's some seats in the back, if you guys don't want to sit on the floor. Back by Pat. If you sit next to an empty seat, raise your hand. Thanks. So that's the first thing. The second thing is that when you read a research paper, or really almost any technical document, whether it's like a textbook or an algorithm on the internet or something like that, there's always going to be stuff that you don't understand. When I read a research paper, I don't understand half the math in the paper, or more. Sometimes I understand none of the math. It's actually the normal situation that you're reading a research paper and you don't understand the math and you haven't seen something that they're using and they're talking about some von Mises distribution. You've never heard of that distribution before. You don't even know, what the inputs and the outputs are. And yet, you still have to read the paper and try to take something away from it. So the experience that you're having where you're reading this paper and there's stuff in it that you don't understand is not an abnormal experience, it's a normal experience. And there might be more things or less things for different people that they understand or don't understand. But that's also normal. Like if I read, I'm a roboticist and computational linguist. So if I read a robotics paper, I usually get more of the math than if I'm reading a computer vision paper or a theory paper or cryptography paper. So what I wanted to give you guys was sort of that experience and then talk about it in class so you could ask questions and we could kind of see some strategies for taking something away from the paper even when you don't understand all of it. And the third thing is, I guess that's the first thing I already said it. I want you guys to see how these techniques play out in the real world. What is one example of some of the issues that they had to grapple to use some of these algorithms in real life. Oh, and I remember the third thing. We want to talk about moving the gradient in better direction. So we're going to talk about stochastic gradient descent, which is a way of selecting what our next state's going to be in a way that's a little bit smarter than this sort of uniform sampling, uninformed sampling. So there's a technical thing which we haven't covered yet, which I'd like to cover in class today. All right. So when you read a paper like this, you don't have to try to understand all of the math. What you really want to focus on is the problem that they're solving. So what's the input to their system? What's the output to their system? What's the state action space? And how do you know whether or not they've solved it? So that's sort of the evaluation section. Once you've got your head around those things, then usually there's some math in terms of how they solved it and what they're doing once they've got that. But you can usually figure out what the input is, what the output is, what the state action space is, without having to understand all of the math, and then take away from the paper, like this is what they're doing. And then if you need to understand the math, if you want to implement it or you want to try a different technique, then you can go and take more time and drill down the math. So we're going to start out with this paper by talking about the input, the output, and the problem formulation of the problem that they're solving. So the paper is called Reinforcement Learning for Mapping Instructions to Actions. And we're going to talk about the sort of problem, and the problem that they're solving is basically following instructions in tech support articles. So here's an article, this is from their paper, this is an example. So what happens is Microsoft makes Windows, and people have problems with Windows. And so somebody at Microsoft writes an article, which is basically a set of instructions to fix the problem that somebody's having. So maybe they want to configure a printer, or they want to fix a problem or erase a file that's causing problems or something like that. And somebody at Microsoft, a person, just wrote down these instructions. And their goal, and the goal of the systems described in this paper is instead of having a person following these tech support articles, they want to have an automatic program that reads the text of the article and then clicks on things in Windows to make it happen. And sort of follows it automatically. So here's an example of these instructions. You click start, here's Windows. So you click start and you point to search, then click for files and folders. And then in the search box, type ms-down-ld.temp, yay Microsoft. And then in the look list, you click my computer and then click search now. And then you sort of keep going to sort of go through these instructions. And what they're trying to do is infer action. So this is like their action language. You left click on this UI thing, which is called the start menu. Then you left click on search, and then you type into the search box ms-down-ld.temp, and then it kind of goes ... Okay, so this is kind of the description in English and pictures of the problem that they're solving. So why don't we try to, going back to our problem formulation language, why don't we try to write it down in terms of states, actions, transition models, goal tests, and path costs. So I'm going to do this on the whiteboard with your help. So what's our state? How do they represent their state? Go back to the picture. Yeah, in the back.
The environment.
Yeah. Okay, so it's a tuple of the environment. I think they use like that funky E. And then the document, yeah. So there's a document that we're reading. So let's say D. So before we go, give me more. Why don't you just tell me what the environment actually is supposed to be? Yeah, it's like all of Windows, like a screenshot of Windows plus all of the memory state and all that stuff. The state of Windows. The state of Windows. And what's the document? The tech support article, right. The words in the tech support article. So the words in the tech support article. So now what else is in the state? Yeah, which sentence? So they call it, I think, J. Is that what they? I just want to use the same variable names that they use. Yeah, J, which is the sentence in D that we are currently doing, following, interpreting, I think I'll say. Interpreting. And what else? Yeah, so W. The sentences we have already interpreted. All right. So why don't we kind of go through an example. So state. Maybe we'll do the actions next, and then we'll go through an example. So what are the actions? This is in section 3 of the paper, if you have the paper pulled up. What are the actions? Yes?
I need the command word.
The command. So what do you mean by command word? I think you're right, but
Right.
Yeah.
The command as in what the document says you're supposed
yeah, so the words
for example.
in D sub I. So let's just say D sub I is D sub J. I need to know what those words are. What else? Yes?
Clicking on UI elements.
Yeah, so clicking on UI elements. So I'm going to take the words, and then I'm going to think about all the things I could do in Windows. So what are some specific things I could do in Windows? Like let's go to this picture here. It's kind of small, but like there's the start menu. So like what are some things I can do in this scene here? Control Alt Delete. Yeah, good. Control Alt Delete. What else? Yeah.
Type things in places.
Type things in place. Let's be really specific. Like what's this thing in this scene right here? I've got the start menu open.
Is that one of the built-in search bar? Windows 7 does.
Yeah, I could click the start. Well, the start menu is already open, but I guess you have to. Yeah, okay. So I can click on the desktop and close the start button.
Or like the keyboard.
Click desktop. Well, let me do desktop one first. Click on desktop to close start menu. What's the keyboard one?
The keyboard start button. If your keyboard.
Yeah. So press. Yep. Press.
Can you try to write just a little higher for the?
Yeah. Press keyboard start button. Are there a lot of actions or not very many actions? Like how many actions do you think there are that I could take in this scene here?
It sort of depends if you can define an action with its parameters or as.
With its parameters.
Okay.
With its parameters, yeah.
then a lot.
A lot, yeah. There's probably 20, 30 just with clicking all the different buttons. And then you sort of imagine all the keyboard shortcuts. There's a really big branching factor. Yeah.
Pull the power plug.
Pull the power plug, yeah.
Like push the power button hard, shut down your computer.
Yeah, well, so that's an interesting one. So I should have, I'm sorry this isn't a bigger screen so we could say. So an action, as they define it, is just one button press. So, or sort of one UI movement.
Power button would be one press.
Oh, I see. You mean push the button on the
Yeah.
on the. Okay, yeah. Okay, I'll buy that. I'll buy that. What I thought you meant was like going to start and then shut down, and then it pulls up that shutdown menu, and then you got to do another action to actually turn off the machine and shut it down. So that would be sort of a depth 2 search in the action space they've defined. Now, of course, we could decide to define different action spaces. The advantage of defining it in the shallow way is that they can programmatically enumerate all of the actions. And that's what Brandavon actually did when he wrote this paper. He ran Windows in VirtualBox, and he used like the C++ Windows API to programmatically enumerate all of the UI actions you could do at any state of Windows. And then you could programmatically execute them and then get to a new state and go through the Windows search tree lots of times. So it's kind of cool, I think. So what's the transition model? I'm going to erase some of the example actions, but I think it's useful. Another kind of trick to understanding research papers is to get as specific as possible with what the variables are. So like an action is kind of an abstract thing, and it's useful to think at the abstract level, but to get a handle on what things are actually happening, what the paper is doing, I think it's good to think about very specific examples. An action is clicking Control-Alt-Delete, clicking on the desktop to close the start menu, pressing the keyboard start button, and all the other things like that. Like we can just hang our hats on what those actions mean. All right. So I'm going to erase the specific examples now, though, to save whiteboard space, and just say clicking, using the abstract one, clicking on UI elements and typing. And they actually don't let you turn off the machine with the power button or pull the plug, but you could think about doing that too. The reason they don't let you is because he can't do that programmatically. He needs a robot to do that automatically. All right, so what's the transition model? Yeah? Question? No, okay. Transition model. What's the transition model? Yep.
It's kind of handled by Windows.
Yeah, it's kind of handled by Windows. So it's like Windows, the Windows code base. The Windows source code. Is that simple or complicated? The Windows source code. Pretty complicated, yeah. What's that? It's pretty complicated, pretty kind of a black box. We don't really know. We can't really write down a succinct mathematical model of this. We just have Windows. And we can do something and see what happens, but we can't really do it in simulation. So this is sort of foreshadowing a little bit what we're going to talk about next week when we talk about local search. If you were going to expand the search tree without actually running Windows, you'd have to write some kind of Windows simulator, where when you did one of these actions, you'd have to know somehow what new state you're going to get. Like what if the action is clicking on the start menu, you have to know that that's going to pull up all of these submenus that you can click on. Your code's going to have to know that. And knowing that without actually running Windows is hard. So Brandavon in this paper, they have to run Windows in order to figure that out. And so that's what sort of changes this from an offline problem to an online problem. So in offline problems, we could know this all offline. With our A* algorithm, we could simulate what it would be like to go visit all of those cities. We could know the cost of the path for being there, we could know our heuristic function, and we could know how good it was without actually getting on an airplane and flying there. In this domain, we don't know that without actually getting on an airplane and flying. So here the flying analogy is we're actually going to have to run Windows and see what the software actually does when we take these actions. So the problem is that that's expensive. It takes time, it takes resources, it takes energy. So it means that we have a huge cost for searching in this tree. Every node that we expand means we have to actually change the physical world in some way. All right, so now what's our goal test? Thank you, but I'm trying to get more. Yeah.
If you did the thing that you were trying to do.
What's that?
Saying this right, but you have an instruction list. Or
Yeah.
Accomplished thing.
Yeah, it's something like we've successfully followed the instructions. Successfully followed instructions. So do we actually have a little program that can tell us whether we've done this or not in the Microsoft domain? We don't. Yeah, you're right. You're shaking your head no. We don't have a program to do this. So we as humans can kind of imagine watching, looking over the machine's shoulder and seeing, as it does a bunch of clicks, and then we can read the instructions and we can say, yes, this actually successfully did a search for that file and removed it, and it worked. And another one where let's say it opened Internet Explorer and starts browsing YouTube, we can be like, no, this did not successfully follow the Microsoft Tech Support article instruction. But our algorithm doesn't know. So there's not any automatic way for the algorithm, for the computer, to know whether or not I successfully followed the instruction. Now this paper talks about two different domains. One is the Windows domain. The second is this game called Crossblock. In that domain, we do know the goal task. You can tell whether or not you've won the game or not. You've reached a goal state in the game. And so that makes the problem easier because you know for sure if you win or you lose. Here, it's very unclear for the algorithm if it won or not. Yes?
It seems like you could use Windows APIs to figure out whether the file actually got deleted at the end of the sequence of actions. Do we not like that because we want to see that it followed a specific path, not just to get there?
Yeah, so to evaluate the system, I forget how many he used. Let me find how many articles. He had this data set of 128 tech support articles. All right. So for any individual tech support article, you're absolutely right. We could sit down and write a program to test whether we've followed the article successfully. And it probably, like 128, if I could do like one every 2 days, then what's it going to be, like 128 divided by 7 or something. So a couple of weeks, 6 weeks or a month or something of writing these very boring programs to check whether or not I followed the article correctly. So it's expensive. I think it would work and it would make the problem easier. But what he's trying to do in this paper is avoid having to do that. So the trick that he's going to use to avoid having to do that is buried in this path cost. So what are they using? I'll write the path cost up here. Path cost. So what is he using for path cost? Yes?
Keeps a score whenever he performs an action in a new state. He checks whether the new action is available, and if it is, then he gets assigns that last action at one.
What do you mean the new action is available?
Tells it like a noisy worker, I think.
So he's checking if the state matches the words in the. I think the most important part of the reward function is this idea of a match between the words in the article and the state. Is that what you're talking about? Okay, so he's basically looking at the tech support article and seeing what words are there. And then he's looking at all of the words that are appearing on screen right now using the Windows API. And you get a point every time the words are the same. So you're basically just trying to keep having overlap between what you see on screen and what you see in the tech support article. So is this an admissible heuristic, or is this going to be, in terms of what our real goal is in terms of following the instructions? Is this always going to tell us what to do in the right way? If we maximize this reward function, will we always be following the instructions? Karthik?
Are we having something like a intermediate goal all the time? Do we test like step by step before reaching the final goal?
Well, we don't know our goal state, right? So we have the instructions from the tech support article, but we don't know. We don't have any function that takes as input a Windows state and says, yes, this state has finished following, or maybe a history of states and said, this has finished following successfully the article. Instead, we have this reward function. And I guess what I want to point out is it's not the same. It's noisy. So sometimes it's going to tell us the wrong thing. They're just kind of hoping that it correlates with successfully following the instructions in the article. Yes?
Depending on how it reads it, if you open up the tech support article a second time, all the words are there again, and it might just read all the words. Like if it's looking for the same words, if you're looking for search or something, it'll appear multiple times. It'll be in a tech article.
So if you like switch, you're like halfway through one, and then you switch to a different one, or
So if it's,
Yeah.
if it's looking for the words that you see in the tech article on the
Yeah.
screen,
Yeah.
as using that as
Yeah.
a point system.
yeah.
If you open up the tech article again on the screen, the
Yeah.
words will be there and it'll see them and it'll say, oh, we're.
I like that. Right. So if it's kind of like a meta thing. If you open up the tech support article in Internet Explorer, you would get a lot of points in your reward function just for opening the tech support article, but not for actually following the instructions. That's a really nice example. I hadn't even thought of that. Yeah. So that's good. So there's kind of like a local minimum, in a sense, in this reward function. You get a lot of reward for doing this, but it wouldn't actually be solving the problem that you want the system to solve. Okay, so what this actually looks like, and I'm borrowing from his slides to show this visualization, is you have some text like, so here's the text, select run after clicking start, in the open box type dcom cnfg, go Microsoft for interpretable things to type in text boxes. And then that corresponds to an action. So the words are clicking start, and the command is in the sort of formal command language that they defined. It's left click on the start menu. And that and so then after that, we get to this new state where they're not showing the window state, but you can imagine like below this, there's a window state where I've clicked the start menu and it's opened up now. And in my document, I've crossed off clicking start. These are the words that this action kind of ate. Okay? So now I'm in this new state where I've crossed off clicking start. Here's my next action. So my words are select run, and the command is I left click on run. So does anybody want to tell me what my new state's going to be after I do action number 2? Somebody over there?
You're gonna have the little run box.
Yeah, so that's my, okay, right. So there's 2 parts to my state. So the Windows state is as I'm going to have clicked on the run box, that's probably going to have the focus, right? So that's good. So what's the other part to my state?
You're gonna cross off select run.
Yeah, so the other part to my state is where I am in the document, and when I update that, I'm going to cross off select run, okay? So this is kind of showing what you'd like it to do. You'd like it to sort of do these things in this order. But observe that there's a lot of, like I could have decided that the first words I'm going to use are select run. And I could map those to some other action like Control-Alt-Delete. And that wouldn't be the right thing to do. It wouldn't we know as observers, as humans, that doesn't actually correspond to what these instructions are telling us. But the algorithm, the program, doesn't know that going in. And what we're going to talk about is how we can make it so that the program knows that. And this is just showing how we can generate all the possible actions. So we were talking about the space of all the UI elements, clicking on all of them and typing here. And so this is just saying, here's all the text in the environments, and then they're saying my computer, left click, select run, my computer, left click, select after. So I can map all of these actions in the environment to all the different words in the document. And then I go to start, and I could do left click, and I could do I sort of get this exponential blow up, right? So this is the number of UI actions, sort of left click, right click, and typing stuff, crossed by the number of, this is the number of UI actions. This is the number of UI objects, and this is the chunks of words in the text, the sentences in the text. So I think they use a parser to get reasonable chunks of words. So they're not going to continue, they're not going to consider like run after as a thing, but just select run and then after clicking start. But even so, there's a lot of them, and we get another factor in our state space. So there's a really big action space that we have to search through to solve this problem. All right, so this is what I was doing before class for what the problem formulation would be. It's basically what we wrote on the whiteboard with less math. So now, why don't we just think about, without worrying about what they did, what I wanted to do was kind of talk about different techniques that we've done in class already and think about how well they might work to solve this problem. So there's sort of 2 questions I'd like to talk about. So the first is whether it would work if we had infinite computation, and the second is whether it's practical, whether we can actually run it with the computation we actually have. So let's think about breadth first search first, uninformed search. So do you think that would find the right answer. So what would a breadth first search algorithm look like in this space? What would it be doing? Yep.
It'd be hard to do breadth first search because you have to revert back to states.
Mhm.
You have to have lots
Mhm.
of states, so you have to
Yeah.
have lots of VMs that every single state
Yeah.
is loading the VM every time.
Yeah.
Or have a way of reverting, which
Yeah.
you have to then teach it.
So let's say I do have a way, not to revert, but I spawn a VM every time I take an action. All right. Let's say I can do that. So I think we're already getting to that breadth first search is going to be really expensive. If every time I take one of these actions, and there's a lot of actions, I've got to spawn a new Windows process to try it out and see where it goes. That's going to run out of memory and computation real fast. But let's say, just for the sake of argument, let's say I did do that. What do you think that breadth first search would find a good sequence of actions? So let's think about what a good sequence of actions means computationally. What would it find after a really long time on EC2? Yeah.
Well, I find something with all the words that's in maps, and like at each step there's words on the screen that match the document, but it doesn't mean you actually found the right thing.
That's right. So breadth first search would find, if we did all that computation and we had the reversing and stuff, it would find the sequence of actions that minimized our path cost or maximized our reward. That may or may not be the right sequence of actions to do in response to the article, and you point out this great example of maybe it would find that I'm going to open up Internet Explorer and search for the words in the article and then pull them up on the screen. But if we can take that away, maybe the hope is that the sequence of actions that maximizes the reward does correspond to doing the right article. So the best that breadth first search would be able to do is maximize our reward, and it would do it, right? It would find the sequence that maximized our reward. It would just be really, 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 really slow. So slow that we can't really actually run it in practice. But it's worth thinking about this case because it tells us, at least in theory, that we've got a state action space that has the right answer somewhere. If breadth first search, if we didn't think that breadth first search given infinite computation could solve the problem, then something's wrong in our problem setup. So it's kind of like a thought experiment to test if we've got things in the right state action space, or a reasonable state action space. So now let's think about informed search, A-star search. So if we want to do A-star search, what do we need to give to our algorithm? I heard it. A heuristic, yes. So what's a heuristic for this problem? I think it's pretty hard to come up with a heuristic for this problem. So you could maybe think of the reward function as kind of a measure of how good our state is, but it's really not, very clear that it's going to like where we are now is sort of the cost of where we've gone so far, but it's really not a good estimate of the future, right? So our heuristic is going to say from where we are right now, what's the cost of the shortest path to the goal? And here our shortest path is minimizing our reward function. So our reward function is so weird and noisy that it's really challenging to come up with a heuristic to estimate it. Yes?
Maybe you could do, if you do some sort of context clues, you might tell whether or not you should stay within the same window.
Yes. Yes.
So like if you had multiple windows on the screen, you might know that way you don't have to explore other windows.
Yeah, so that's actually very similar to what we're going to do in order to solve the problem, but we're not going to do it in the context of A-star. So the next thing we're going to talk about is hill climbing and how we can use context clues to get a good, not heuristic, but reward function. So the problem with A-star is that using that to get a heuristic is pretty challenging. There's another problem with A-star. It's related to the problem we had with breadth first search. Yep.
Well, we're still expanding those, so we still have to keep planning.
Yeah, we're still doing this thing where we're expanding and then backtracking, and we either have to spawn multiple different Windows machines, which is really, even if it's not as expensive as breadth first search, in the limit, it could still be as expensive if our heuristic is bad. And expanding, opening up one of these VirtualBox machines is not a trivial thing. It uses lots of memory and it takes lots of time. So A-star is probably where we have multiple search threads going, and we're switching back and forth between them is probably not the best way to go here. So now we're going to talk about hill climbing. So what do you guys think about doing hill climbing? Local greedy search. So what's that going to look like if I'm in a, yeah?
Okay, it'll pick the ones with the most overlapping words, and it won't have to store a ton of stuff in memory.
Yeah, so my hill climbing is only going to be expanding one node at a time. It's going to think about all the next actions I could take. It's going to pick one of them, not all of them. And it's just going to go there and hope it's the right thing. So that seems like at least we could run it. Like the other ones, we might not even be able to run more than 2 or 3 nodes before we run out of memory. This we can actually implement. We can do it. But the question now is our reward function. So what are we going to be trying to optimize with hill climbing? So what if we just tried to maximize our reward function directly? What might happen? Yeah.
You might find a text box that we can open and just start typing out the words that we're looking for.
Yeah, so we could have these kind of local minimum types of failures. The other thing, and I haven't really set up for this, so maybe I'll just say, is that we might get to a place where there's actions we need to take that will eventually get us to a place that has high reward. Like we're in a local minimum. But right now, we don't see them. So maybe you have to go 2 or 3 steps to find a lot of overlap, if you assume your overlap is a good signal. But right now, if we just look at the next step, there's not very much overlap. So in order to, so this is the approach that they're going to take to this problem. They're going to do hill climbing, but they're not going to do it directly in the reward space that they define. They're going to do it, they're going to basically come up with, magically, we'll talk about the magic next, but like for now, magically, they're going to come up with a better reward function, cost function that they can use in order to choose actions. And hopefully, it'll allow the thing to make smarter decisions without having to do as much search. All right, so this is sort of the question. Where do we get this reward function? What should we use for our reward function in order to have a machine that's making good decisions? And their answer is, the way that we're going to write it mathematically is as a policy function. So this is a distribution over the actions. Remember our actions, if we go back here, our actions were all of these things. We're going to have a distribution of the action to pick given the state, this current state of the world, and also where we are in the document. And our policy functions, if we had a really good policy function, it's going to look like it's going to look like the algorithm is almost, has precognition. It just knows what the right thing to do is. If we have a bad policy function, it might do something completely terrible and not earn very much reward. So we're going to talk about how we can explore the space of possible policy functions and come up with a good one. And the way that once we have one of these policy functions, we can it really looks a lot like hill climbing. I'm just going to think about all the actions I could do. I'm going to do an argmax over actions of this, and pick the one that my policy function gives the highest score to. Does that make sense? Yeah. So once I have the policy function, it's just hill climbing. A lot of the technical machinery, the math that we're going to talk about next is, okay, if I had this function, everything would be good, but where do I get it from? How do I come up with this magical function that's going to solve all of my problems? So here's a sort of summary of this. So I'm going to choose my actions according to the policy function, and if I have a good policy function, I'm going to earn lots of reward when I go off and execute. So the sort of learning problem, so now what we're going to talk about is a second formulation of a problem. So the problem formulation we wrote up here, this was like what they really want to do. Like when you send this machine into the wild or something, this is the problem we really want to solve. And the approach that they're going to take to solve it is by finding this policy function, P of A given S. So this is a different problem. So in this problem here, we're clicking on things and we're trying to earn reward. And we're searching for the sequence of actions that gives us the maximum reward. The thing we're searching for is a sequence of clicks, a sequence of states through the space. Here, the thing we're searching for is this policy function, P of A given S. We're going to define a space of all the different possible policy functions. It's actually not going to be all the different ones. We're going to define a space that's easy to search through. And then we're going to try a lot of different values. We're going to score them somehow, and we're going to take the best one and then use it in our other state space and see how well it works. So the next thing I want to do is talk about what the problem formulation is for the learning problem. So here's what they're going to do. They're going to take a lot of tech support articles. So they have a data set of 128, and they're using 70 of them for training. So they're going to give this machine a lot of these tech support articles. They're going to give it Windows. So he actually loads it up in VMware, and the algorithm gets to play around with it. Then we're going to do the magic, which we'll talk about next. And then at the end of this process, profit, right? This is the /dot formulation for a successful startup. And here, profit's going to be P of A given S, right? So at the end of this magic that happens inside of here, we're going to have a P of A given S that hopefully, we don't really know how sure we can be about this. It's going to find a local maximum, but that hopefully does well at this problem. Now, I say hopefully does well. Like for this paper to be successful, they actually have to demonstrate that it does well. So they come out with this policy function. Then they try it out on a different data set of articles, and they had to, for those articles, they had to annotate. Sorry. They had to annotate what the right answer is in order to see, is it really doing the right thing? So they had to do, in order to do this assessment, they had to actually do these annotations that I said we kind of didn't want to have to do. It's kind of an interesting thing with research papers. Like the point of this algorithm is we don't want to do these annotations, but to actually see if the algorithm worked, we have to do it anyway. So I wanted to sort of prelude that the evaluation is important, because when I put these question marks, it makes it seem like it's too magical. All right. So let's talk about the problem formulation for learning. So I'll erase this one. All right, so what we want is a P of A given S. And there's kind of a trick we do in machine learning to say, so in general, there's like an uncountably large number of functions that this could be, right? There's like any function we could dream up for assigning probability to an action given a state that normalizes and sums to 1 and all that would be valid. And that space is incredibly hard to get our hands on. So instead what we're going to do is assume that this function is in a particular family of function that's sort of nice. It's differentiable and stuff like that, and it looks like a probability function. And I'll write it down later. And it's parameterized by some numbers, which we'll just call theta. So theta is just a big vector of numbers. V1, V2, let's see, V3, V sub k. And this is what theta is, okay? Now, I haven't told you how we're going to use theta in P of A given S, but there's lots of different ways we could use it. They picked one. This is sort of a modeling decision, and if you take a machine learning class, you'll learn about lots of different ways that we could parameterize this. And even in this course, we're going to talk about naive Bayes and logistic regression, and sort of there's lots of mathematical tricks with lots of trade-offs and in terms of what goes here. But at the abstract level, it's just some numbers that we're searching for. So now let's formulate the problem, the learning problem, where we're going to take lots of tech support articles, load up an instance of Windows, and we're going to search. I haven't said how we're going to search. That's going to be the math. And then we're going to get some profit. So what is our state? In this learning problem? What are we kind of searching through? What do we want? Well, that in our other problem where we're actually trying to pick actions, we want actions. This is the learning problem. So what we really want at the end of the day is P of A given S. And what I'm saying is we're going to parameterize this with this variable theta. So what's our state? Yeah. Yeah, the value of theta. It's theta. So some current value for theta. Now, what are some actions? Yep. Yeah, changing theta. So theta gets theta plus d theta. All right. Now, really big action space. We're going to talk about how to. This kind of looks like simulated annealing, maybe. Like we sort of have this choice of where do our d thetas come from, and that's like the magic of this whole thing. Yes.
How many values does the theta vector have?
I haven't told you. So we'll talk about that So at this level of abstraction, you don't need to know. With the particular choice of models that they're making, I think it has like 4,000 or so particular values in the vector. And that's pretty typical for a machine learning problem in computational linguistics.
They represent possible actions?
I haven't told you. So it's each value of theta corresponds to a different P of A given S. So each possible value of theta, I can plug it into the P of A given S. I haven't told you how, but I can. And then that will give me a function that takes as input an action and returns a number for how likely it is that I should choose that action, given the state of Windows and where I am in the document and the sentence that I'm currently processing. So for example, to bring it all the way down to an example, if I'm, the goal of this P of A given S is, is if I'm trying to do select run, and it goes through all of these different actions, the perfect P of A given S would assign 1 to, let's say clicking start, because that matches the picture. If I'm processing clicking start, and this is my state, and these are all the actions, the perfect P of A given S, like the best one, would be to assign probability 1 to this action and 0 to all of the other actions. And other things would be less good, because here we can look and know it's the right thing. And with different, and the goal of our theta is going to be to, in general, take as input one of these actions and states and give you some number. Hopefully good numbers, but maybe not. And for different thetas, they'll assign different numbers to this action. And we're going to try to find the theta that assigns the best numbers. And we'll talk about what best means in math next. But intuitively, what best means is giving a lot of probability to this and not very much probability to all these other ones. Okay? Okay. All right. All right, so then our transition model is kind of the same as our actions. Like it's actually doing this update. Transition model is the plus. Yes, Karthik.
Can you consider theta as some kind of representation of the path that the system has?
Maybe I should have done this in a different order. I didn't want to put too much math in too early. For those of you who've seen log linear models or like naive Bayes machine learning, it's a feature vector. So it's going to be different. Each data value is going to correspond to a feature weight for the mapping between words in the tech support article, the word that we're being processed, and the feature and stuff about the action that I'm taking, the name of the action, the UI object that I'm taking. So it's going to be able to learn things like the word start in the text, and clicking on the button start are good things to do. It'll assign high, if everything is a good theta, will assign high value to that, and that will correspond to high probability mass in the action. So we're going to go through the math of this later in the semester in more detail. So what I'm hoping now is to give you guys a taste of what it's like or how it plays out. All right, so what is, I guess maybe you've seen it already, but what is the path cost? So what's our goal test? What's our goal test? This is also a little, it's kind of like the one from before. Yeah? You're shaking your head? You have no clue. Well, that's exactly the right answer. We don't know what a good goal test is. Maybe it's like a theta that gives us the best policy, but we, just like in the Windows domain, we don't have a good way of knowing just from theta whether it gives a good policy or not. So what we do have is a path cost. So if we have a particular theta, we don't know for sure if it's the best possible theta. Like I can look at this particular example and say, well, the best possible theta is the one that assigns probability 1 to this and probability 0 to all the other ones. But there's a lot of other, like what if it assigns 0.9 to this, and then all the rest of them are drawn at uniform from the 0.1 that was left over. That's probably pretty good. What if it assigns 0.0001 to this? Is that good or not so good? That's not so good. So even though we kind of think maybe the best one would be assigning probability 1 to this, there's some kind of ordering that we can impose on these data. And we can actually quantify this by trying it out. So we can, for any particular theta that we have, we can do hill climbing with this policy, and we can see how much reward we get. Right? We have the reward function from checking how many words match the document. And if we get a lot of reward, it's a good theta. If we don't get very much reward, it's not so good. And we can actually do that. We can actually write a program to do hill climbing, open things in Windows, and we only have to have one virtual box to do it. And then we can look at that trajectory, we can compute our reward function, and we can do this over all of the documents in our training set, all 70 of those documents. And we can say, okay, with this theta, with theta 1, we got 100 reward, and with theta 2, we got 75 reward. So theta 1 is better than theta 2 on my training set. So that's what we want to do, is find the theta that maximizes our reward. So here's the problem formulation, the reward earned on the training set with that theta by actually trying it out and using it to do a hill climbing search to pick out a document. So the way that he did the learning is you basically, there's an outer loop here, for each document in your training corpus, you observe the current state of the world, so where you are in the text, in the environment. You select an action based on theta. So with our P of theta, we can do hill climbing search and select an action. And then once we have that history, we can receive a reward and then update our parameters. And what this really, you can think of this at a very high level, is simulated annealing, right? We're going to select an action, we're going to see how much reward we got, and then we're going to decide, in our simulated annealing, we're going to decide whether to stay where we were or go somewhere else. Here we're going to do something more complicated, but at an abstract level, it's going to decide where to move our theta to get to a better theta. You have a question? Okay. Anybody have any questions? All right. So and the way that we're going to do this is stochastic gradient descent. So P of A given S, and I did this on the whiteboard, P of A given S and theta. So we're going to make this assumption that it has this parametric form, which I haven't told you what form, but it's going to be parameterized by this theta. And then go find the theta that maximizes the reward. So find theta that maximizes the expected reward. And the name of the algorithm is policy gradient algorithm, and that's sort of like we haven't even really defined reinforcement learning yet. So this is kind of the technical names about where this all fits in the larger field of AI and in RL, but without even formally defining theta policy gradients and reinforcement learning, you can just think of this as stochastic gradient descent on theta. We're going to be bouncing around in the space of different thetas randomly, and we're going to be trying to find the one that gives us the most reward. Okay? All right. So the next thing I want to do is kind of do some math to write down what this actually looks like. So we talked about how we have a way to assess. What? Okay, excellent. Sorry, Pat. So we have a way to compare different thetas. So can we write down in math what that actually looks like? So I was sort of saying we can try out theta and see how much reward we would earn. So in math, what does that correspond to? Yeah. Yeah, so you're one step ahead of me. What are we going to take the derivative of? Yeah, the cost. But it's not exactly the cost because we don't quite know what's going to happen when we go off and execute our action. There's a really big action space, and and then there's some uncertainty about that. So it's actually going to be the expected cost. So the expected reward. It's like a sign thing. So it's the expectation under the history of all the actions you could take of R of H. So if I put that up, so the argmax just says I'm going to search for the theta that maximizes my expected reward of running on a particular document. So here H is like the history of the actions that I took as I was following the instructions with this policy, with this particular theta. So if you remember, we were really talking about P of A given S. So here's our update. I did this in the wrong order. So we'll talk about how we can go from H, this whole history, the sequence of actions, to a particular action, P of A given S. So the way that we're going to be searching for theta is we're going to update by taking the derivative. So the person back there who said taking the derivative is and updating, that's exactly right. We're going to take the derivative of this with respect to theta. And then that's going to tell us the gradient. So the gradient is basically saying, what direction do I go in? What's a good direction to go in? Let's not just sample uniformly in a disk around my current place, although I could do that. People do that all the time. But let's take the derivative with respect to theta of the reward and then try to go in that direction. Because that's a direction that sort of, it's basically trying to, looking at those particular examples where I didn't earn reward and I could have, and like knocking down the feature weights that prevented me from doing that and increasing the feature weights that made me want to do that. Carther?
Can we just explain the Boris equation?
Yeah, this argmax up here? Okay, so argmax is a mathematical notation for an optimization problem. So in words, it means I want to find the theta that maximizes this thing. Okay? And this thing is the expected reward. So if I take those parameter vectors and I just run them on an article, or run them on 70 articles, it's saying what's the mean reward that I'm going to get with those parameter vectors? What's the average reward I can expect to get with this theta? And if that's a high number, then I have a good theta. If it's low, then I have a bad theta. So it's mathematically quantifying how good my theta is. And we'll see as we go through the semester, there's different ways. A lot of machine learning problems come out as these optimizations where you're optimizing something, you're minimizing something, or you're maximizing something. And the something changes and the sort of details change. But the idea that you're optimizing is constant. Yes?
So we haven't necessarily defined the dimensions of the vector for theta?
That's right. We have not defined the dimensions of the vector for theta. So we're going to do that next. Yes?
Just to clarify,
Yeah.
the expectation is for running like a full series of actions, not just...
That's right.
Okay.
Yeah, so we're gonna break that down now. So to actually take this derivative, the first thing we're going to do is write it as a summation over all of the possible histories. So all of the possible different sequences of actions that I could take. And then I'm going to take the reward of that particular history and the probability that I assign to that history. Is this big or small? All the possible histories here. Huge. Yeah, this is not made my life better yet. Okay, but it's sort of on the road to making it better. So then the next thing we're going to do is factor. So I can write this in terms of a product over the actions in H. So H is basically a sequence of actions. And I can say, given my state, given my current state and theta, I can pick the next action. And then given that action, that takes me to a new state. So this gets us from H to a particular action, so sort of answering your question. And I need to do this in order to actually take this derivative. So the sort of abstract form of this parameter update corresponds to a specific update. In order to get to the specific update, I have to tell you what I'm going to assume P of A given S and theta is. So here's sort of what taking the derivative looks like. So this is sort of all generic. I don't need to know what P of A given S theta is. But now to take this derivative inside, I have to tell you what it is. Here's what it is. You guys have kind of been waiting for this maybe. I don't know if it's useful to show this at the beginning or not. I was kind of hoping to gloss over what? You're laughing. What's the question? That's the question. Yeah, good. That's the question, yeah. So a lot of machine learning is like, what do I actually do for this? And we'll talk about, you know, all like, some of the different choices. Some of which are probabilistic. People use decision trees. They use, you know, there's lots and lots and lots and lots of different choices. This is one of the most popular, and a lot of it's fads. So like people do deep learning these days. Have you ever heard of that? Deep learning? It's like a new thing in AI, which is like a renaming of a very old thing. Which, they used to be called neural networks, but they renamed them to deep learning. And it's a different. It's not this one, but it's kind of similar. A different thing to put inside here, and everybody's all excited about it. Now Google just bought this company that does deep learning, and everybody's like, all the machine learning people are like, what's Google going to do? Is it going to make is it going to make the AI overlords or something? And it's all because of a different mathematical trick that goes in here. So even though you may not understand, and I'll talk a little bit about what the advantages of this particular form are. Even though you may not understand what this is doing, why we chose this particular form, it's more important to take away this left side, this thing that's picking the probability of an action given a state. Okay? It's more important to think about the input and the output rather than the specific parameterization. A lot of time, so I'll say that we don't have that much time left though, so I'll also say a little bit about what the advantage of this particular form is. This is a log linear model or logistic regression model. A lot of times when you see things here, there'll be the summation on the bottom of the same thing on the top. This pattern where this thing on the top and the same thing with an A prime on the bottom summing over all A's. Anybody want to guess what that's about? Why we have to do the summation and the division? Yeah. Yeah, it's just a trick. It makes it sum to 1. So this is supposed to be a probability. No matter what theta I pick, no matter what numbers I put in my theta vector, this will always sum to 1. Okay? So then the other piece of the trick is this phi. So I've introduced this new thing here, this phi function. And that's going to correspond to the feature. So I alluded to it before. Each of these thetas is going to correspond to a feature weight. So the next slide kind of gets into this. So I'm going to define a real valued function manually. I'm going to write a bunch of programs to do this. That takes as input a state and an action and returns a value. It could be a real number, or it could be a 0 or a 1. So let's just think about zeros and ones because it works fine. It works fine with zeros and ones. So what are some features that might be useful for this problem? What might help us pick a good action? If I'm sitting down, I want to encode a piece of information that's going to help the computer make this decision. Yeah.
Whether or not the start menu is open?
Whether or not the start menu is open, yeah, good. What else? That was good. Yeah.
Whether it's expecting like text input.
Yeah, whether there's a text area or not a text area. Yeah.
Whether or not you're in a modal dialogue.
Whether or not I'm in a modal dialogue. Yeah. So that's, and we could think of a lot more, right? Yes, we could think of lots of these kinds of tests. And that's what Bronavon basically did. So here's some of the features that he used. Whether an object is visible, whether it's in the foreground, whether it's something they previously interacted with. So maybe you want to keep interacting with things that you interacted with before. Whether it appeared after the last action. So maybe you want to click on things that you clicked on before. And total number of features is 4,400 some. And what our thetas are going to do, so each one of these features is a phi sub I. And what our theta is going to do is learn which features are good and which features are bad. So you can just give it all the features you think might be good and all the features you think maybe they're not so good, but who knows? I'll just throw it in there. You just throw in your 4,000 some features and then let the algorithm figure out the theta values that give you the best P of A given S. Does that make sense? Yeah? I see some head nods. Yeah?
Oh, we only have like 100 documents, but we have 4,000 features.
Yes.
Is it a problem or something?
Yeah, it can be a problem. So what kind of saves us is that Windows is so big. So even though we only have a few hundred, I think they use 70 documents in the training set. Yeah. Each of those documents has, I don't know how many, but let's say between 10 and 20 sentences. And each one of those sentences, like you're choosing from among all these different actions. So they really, like if you take the cross product of those documents with those sentences, give you all of Windows, that's actually quite a lot of data that you have. But we're pointing to is a very important problem in machine learning that happens a lot, overfitting, where if we don't have enough documents, we'll basically memorize what to do with the documents in our training set, and we won't learn how to generalize to our test set. So it's an important issue. I don't think he's got that problem, but we always have to think about it when we do these kinds of problems. All right, so we can kind of go back here. So it turns out if you plug this into this equation and you take the derivative of e to the x is itself with the chain rule and stuff. So if you and to actually do this, it's like pages of algebra. So I wrote a paper that extended on this paper, and I had a LaTeX file that had like 30 equations of me taking my derivative to go from here to here to actually get the derivative value. In the paper, they just skipped it because I don't want to say it's just algebra because it's a lot of algebra, but they don't need to go into the whole detail of where it comes from. So don't worry if you don't see immediately how you get from here to here. I'm just asking you to trust me that if you do take this derivative with this function, you get this. Okay? If you really want to, you can take it yourself. And when I was writing my spin-off paper, I did that. So the first thing I did was I took this derivative just to make sure that I could understand the algebra and how they did it. And then I had a modified version of this function, and I had to take a more complicated derivative second. So don't worry if you're not following all the algebra. I didn't even bother putting it up because I feel like it's at a lower level than we really want to be. What is worth looking at is the form that this parameter update takes. So this is the derivative with respect to theta, with respect to one particular theta value and one particular feature. So let's say the feature that I'm going to click on the object that just appeared from the last action, and then subtract. So what I'm going to do is take the value of this feature, whatever it was. Let's say I clicked it, so it was 1. And then I'm going to sum over the value of this feature weighted by the value of the distribution. So the e to the x kind of makes this term appear in the derivative. So that's why it appears again. I'm going to sum by the expected value of this feature with respect to all of the other actions I could have taken. So it's kind of an error measure for how far away I want this feature value to be from from where this feature value actually is to where I predicted it is. So that's why intuitively, without going into the algebra, that's why it's kind of nudging me in a good direction. And what I actually do in my parameter update, and this works like this comes in the derivative, is I have to multiply this by the reward. So if that was a good thing, like the action that I picked was a good thing, I want to move it in that direction. And if it was a bad thing, I want to move it in the other direction. So that's what the R is going to do. And if it was a really good thing, I want to really move it in that direction. So I'm scaling by the reward. Does that make sense? All right. So we can sort of come back to our learning algorithm. And maybe you guys have a sense of how it works. It's kind of going through each document. This is one more thing that's kind of important that I glossed over, which is this. Sorry, I know we're almost out of time. Which is the summation right here. This summation right here. So we said this summation isn't tractable. So what they do to make it tractable is they just draw a sample. They approximate it by trying to do a bunch of things in Windows. So they'll draw like 2 or 3 samples of histories with that particular policy. So then each H, there's only 3 H's that they have to consider. And then for each history, they know the reward. They know the probability that the model assigned to it. So it's really easy to compute that. And what's really amazing is that even though the number of possible histories is like mind-blowingly big, they're able to get really good performance by sampling like 2 or 3 histories from Windows. So that's kind of one of the things that when I read this in the paper, I was like, wow, like how could that possibly be? And yet it is. Like their results back up that the sampling thing was successful. So the point of mentioning this is I want to again show the power of these kinds of stochastic hill climbing approximation techniques. You can really often get a lot of mileage by making these kinds of approximations. So to finish up, let me go back to the slides. They had a bunch of results, where they're comparing different algorithms for selecting what action to take, and this is by these different the percent of actions correctly mapped is by annotating the correct action that you were supposed to take for each state. So they had to go through and annotate to get these numbers, and then the 65% is how many of the time their algorithm with this sampling two things and doing the stochastic gradient descent was able to pick the correct action from this huge space of possible actions. So what this is saying, we can talk about the baselines later if you guys want. This is saying that it kind of worked. If you annotate everything, you do better, but without having to annotate very much, they were able to get really good performance. So I hope this was interesting and not too much stuff you guys didn't get. Just to summarize, what I wanted you guys to get was reading a research paper when you don't have all the background, online and offline search. The idea that we have one problem formulation for inference, a second one for learning, and that's okay. And doing this random stuff can be really cool, really effective. Thanks.